This is a video about limiting reactants. When we do a reaction, we are always going to run out of one of the reactants and then the reaction will stop. That's what a limiting reactant is. So I have an analogy for you. Like if I were making burgers, turkey burgers, veggie burgers, whatever, and you look at, this would be kind of like my chemical reaction. So I would have, let me grab my pen. You know, these burgers plus the buns plus the cheese slices plus the tomato, those are my reactants, and then that would yield the assembled burgers. And then you can see that I ran out of, what did I run out of? The patties. So this is my limiting reactant, the one that made me run out and stop making burgers. And then that means I'm going to have excess of these other reactants. I should have more tomatoes in excess. I've only used 3, so I should have like 4 extra tomatoes left over. So that's just an analogy to kind of help you to start to think about what an excess reagent is. The other thing I want you to do is think about the lab that we just did. In the lab that we just did, remember we took iron and copper sulfate, and then it was a single replacement. We made copper, and then it was either FeSO4 or Fe2SO43. The point is, though, when you isolated your copper, you did the decanting, you were pouring off excess blue. So this was my excess reactant. This iron is the one that was my limiting reactant. And you remember how I had them pre-masked for you in the little containers? I did that on purpose so that I knew this would be your excess. So I knew you'd be pouring off blue. So the iron all reacted and there was leftover copper sulfate. And that was one that was really visible for us to be able to tell. So a limiting reactant is, it's the reactant, like I was saying, it's the one that you'll run out of and it'll cause the reaction to stop. All calculations are based on that limiting reactant for stoichiometry. And I'll show you guys that, how that works in just a second. The excess reactant is the one that won't all get used up, and there'll be leftovers of this, which is somewhat wasteful. So if you're in industry and you're trying to do a reaction, you don't want so much excess. You'd want to figure out your limiting and then you can try really hard to use exact amounts of each so you don't run out of either, but most likely you would run out of one before the other, but you don't want to have a huge difference. So here's an example of a problem that we can do. And this is hydrophoric, hydrogen fluoride. It's not hydrofluoric acid until it's dissolved in water, which is something you don't need to know. But anyways, this is how you can etch glass. I don't know if you know what I mean. Like sometimes you'll have like a design that's kind of grooved into the glass. This is the reaction that happens. The glass is the silicon dioxide. So these are the steps that we're going to follow to determine which one is a limiting reactant. So it's either going to be this one or this one. It's always a reactant that we're talking about first. So let me get myself out of the way. I don't know where to put myself. Maybe over there. Okay. So there's some steps that I recommend that you use. And if you Google how to do limiting reactant problems, you will find many different ways to do this. This is the way that I feel is the simplest. If you want to use another way, as long as you show your work and you're getting the right answers, go for it. And then I can just follow your work. But this is the way that I do it and Miss Snyder does it. So the first thing we do is, if the reactants are not already in moles, we would convert them to moles. So in this problem, we don't have to, but on the next one, we will. Then you're going to pick one of the reactants and convert it to moles of the other reactant. So let me think which way I'm going to go. So I'm going to just pick the 4.5 moles of SiO2, and I'm going to convert it into moles of HF. You could have went the other way too, but I just randomly pick one of them, convert to the other. So when I do this, I'm going to use my mole-mole ratio. So I have 1 and a 4. So I'm going to put, 4 moles of HF on the top and 1 mole of SiO2 on the bottom. So my moles will cancel and I'll end up in moles of HF. So I'm going to bring my answer down here. So I would get 18 moles of HF. That's how much I would need in order to react with all 4.5 moles of the silicon dioxide. So then I go and I ask myself, hey, do I have 18 moles? So I actually ask myself, do I have this amount? And my answer this time is no. So because my answer is no, that means that I'm going to run out of HF first. So that means HF is my limiting reactant. I don't have enough to react with all of the silicon dioxide. So I'm going to have leftover silicon dioxide, and I'm going to run out of HF first. So that's how you determine it. We could have went the other direction too. If I had went the other way, I would have started with my 6 moles of HF, and I would have converted it to SiO2. So my ratio would have been 1 to 4, and that would have given me 1.5 moles of SiO2. And I would ask myself, do I have this? Do I have this much? Can I react all of this? And the answer is yes, I have plenty. So because I have plenty of this, it means I'm going to run out of this one. I know this is weird, but you're going to practice it a lot. So in fact, let's do another problem. So this problem is what happens like for if you have like a propane grill. It burns propane. That's what C3H8 is. It reacts. It's a combustion reaction. Reacts with oxygen, produces carbon dioxide and water. So in this question, they're telling me that I have 3.0 10 to the 23rd molecules of this and 25 grams of this. And then I'm being asked, who's the LR, who's the ER? The excess reagent or reactant, the limiting reagent or reactant. So the first step I'm going to do is I'm going to convert each of these to moles. So this is just, we're not doing the stoich yet, but I'm just going to take my molecules of C3H8, and you could pause this and do this on your own if you wanted. I'm going to go to mole. 10 to the 23rd molecules in 1 mole. So when I do that, I get 0.50 moles of C3H8. Then I'm going to do similar with the grams of oxygen. So 25 grams of oxygen, and I'm going to go to moles of oxygen. And when I do that, by the way, everything cancels. When I do that, 25, I get 0.78 moles of oxygen. So that's the first step. The second step now is we're going to convert one of these moles of C3H8 to moles of O2, or moles of O2 to C3H8. I'm going to start with the moles of O2. So I'm going to take my 0.78 moles of O2, and I'm going to convert these moles to these moles. So I'm going to do a mole-mole ratio. So I'm going to put my 5 on the bottom. So that's my coefficient right here. And I'm going to put my 1 on the top. So when I do this, I end up with my moles of C3H8, which are 0.16. So I just did step 2. Then I have to ask myself, do I have this much? Because this is how much I would need to react with all 0.78 moles of the oxygen. So do I have 0.16 moles of C3H8? I have to look at my moles up here, and I can see that I do have enough. So because I have enough, that means I'm not going to run out of the C3H8. I'm going to run out of oxygen. So oxygen is my limiting. The C3H8 is my excess reactant. So now the next step is, now I might be wondering, well, how many grams of this do I have and how many grams of this would I make? And I was given in the beginning question, I'm given 2 different numbers to start with. And the only one that dictates the amount of each of those products that I can make is the limiting reactant. So I'm going to use the limiting reactant to solve any other stoichiometry problem. So the next slide, I'm going to be using and starting with the 25 grams of oxygen. I could have started with my moles too, because remember I had already converted, but I'll just do it this way. So I'm going to go to so I'm using my limiting, and I'm going to convert it to grams of CO2 first. So I know, I've already done this, but I'll do it again. So 32 grams. And now I'm going to use my mole-mole ratio. So 3 moles of CO2 from right here for every 5 moles of O2. And you can see canceling along. And then 44.01 grams of CO2 in 1 mole of CO2. So when I do this calculation, I'm going to get 20.6 grams of CO2. And then you could pause the video and try to solve this other one. So again, we're trying to figure out how many grams of each product that we're going to actually make. And we're using the limiting reactant to solve this. So I would pause the video, try solving this one. It's good stoic practice. And then we will move on after that. All right, so hopefully when you solve that one, you can see we're going to go to grams of water. And we should get with, I don't know why I'm going to 3 cigs. I guess I should only go to 2. I can't remember if the 25, okay, yeah. So this should really be 21 and 11. Okay, one more problem. So sometimes we ask how much of the excess reactant is there going to be? When we do that, we have to take the limiting and convert it into the excess reactant first. So if we haven't already done that in a previous problem, so what we would want to do is, and we maybe did it in the previous problem, I can't remember. We did. So I took my 0.78 moles of O2 and I converted it into moles of C3H8. And then when I did that, so sometimes if you, just depending on which one you pick, you may not have already done this step. So the first thing you would do is always start with your limiting and convert it to the other excess reactant. So in this one I get 0.16 moles then. Remember, that's how much I will actually need to use. Then I go to the beginning problem and I know that I started with 0.50 moles.